Look around you. A spool of copper wire, a pressurized oxygen tank, the silicon chip powering your phone, and a heavy gold ring. At first glance, these objects have absolutely nothing in common. So what exactly unites them at a microscopic level? Despite taking on completely different physical forms, every single one of these items is constructed from the exact same universal building blocks. We call these blocks elements. This animation shows what happens when we zoom in past the macroscopic level. An element is a pure substance, the absolute simplest possible form of matter. It is incapable of being broken down any further by any chemical reaction. Identifying these unbreakable foundational pieces is the crucial first step to reverse engineering the materials that make up our modern world. Right now, scientists have identified exactly 118 distinct elements. That is the entire universal toolkit. Some of these are pulled directly from the Earth's crust, while others are synthesized in laboratories. Synthesized elements are human-made, created by colliding lighter atoms together at high speeds, but they are completely real and functional atoms. To keep track of these 118 ingredients, we use chemical symbols, like Fe for iron and Cu for copper. These symbols function as a standardized international code, allowing scientists across the globe to communicate without language barriers. Managing a toolkit of 118 unique ingredients requires a rigorous sorting system. Engineers need to know exactly which material is suited for a specific human application. This diagram shows the periodic table, which acts as the ultimate scientific sorting tray for all 118 elements. Scientists divide this table into 3 distinct zones based on the observable physical traits, or personalities, of the elements: metals, nonmetals, and metalloids. To figure out an element's personality, we subject it to physical stress tests. The first is the hammer test, which evaluates structural integrity. As this animation demonstrates, when you strike an iron block with a hammer, it doesn't break, it flattens into a thin sheet. This is malleability. Now strike a lump of sulfur with that exact same physical force. It instantly shatters into dust. That is brittleness. This simple stress test instantly sorts our toolkit. We can easily separate the materials that can be shaped to build structures from the materials that cannot. Our second stress test is the circuit test. This evaluates how easily an element allows energy to flow through it. This schematic shows a basic battery and bulb circuit. When we connect them with a copper wire, the bulb lights up brightly. The copper allows the electrical current to pass, proving it is a conductor. Conversely, if we place a piece of coal in that same circuit, it completely blocks the electrical current. Materials that stop the flow of electricity are known as insulators. The third and simplest stress test is the eye test. We evaluate how a material interacts with ambient light. Raw silver has a highly reflective, shiny surface, a property known as luster. Carbon, on the other hand, absorbs light and appears dull. We check for malleability, test for electrical conductivity, and observe the luster. These 3 specific diagnostics allow us to definitively categorize any raw element we pull from the Earth. That brings us back to the first and largest category on our map, metals. Based on our tests, we know their profile. Metals are generally hard, highly lustrous, incredibly malleable, and excellent conductors of both heat and electricity. There is one glaring rule-breaking exception to the metal family. Mercury uniquely exists as a fluid liquid at room temperature. The second category is the nonmetals. They are the exact opposite, dull, brittle, and poor conductors. Yet, elements in this group, like oxygen and carbon, are absolutely vital for biological life. Finally, we have the metalloids. Elements like silicon live on the border, possessing hybrid traits of both metals and nonmetals. By sorting elements into these 3 distinct families, we can accurately predict how an element will behave without having to individually memorize the physical traits of all 118. Let's look back at those everyday objects from the beginning, but this time with X-ray chemistry vision. That copper wire wasn't chosen at random. Its metallic traits of ductility, the physical property that allows a material to be stretched into thin wires without breaking, and electrical conductivity make it the perfect power conduit. That silicon chip operates exactly because of its hybrid metalloid nature. It acts as a precise, controlled gatekeeper for electrical signals inside your phone. Knowing an element's category also lets scientists predict chemical reactions, like how certain metals will inevitably corrode or rust when exposed to oxygen and water over time. Classifying an element as a metal, nonmetal, or metalloid provides the predictive power necessary to engineer the precise materials found throughout the modern world.